Perfect. All right, so I'm from Thingsquare. We're a Stockholm-based startup, bootstrapped. And what we do is that we help our customers build connected products. We offer a complete system, which is, all the parts from the software running on the devices to server backend in the cloud to apps and APIs so that you can get your data, etc. So through this talk, we're going to go through a few levels. We're going to look at the very deepest parts of wireless. I think wireless is just a very, very interesting topic, and it's just fascinating how it works deep down. But to begin with, so let's skip these marketing slides here. So what you see is basically us everywhere there, hopefully. There's a nice effect there. I think I added this marquee tag. So to begin with what are connected products really, and do we really need them? And well, we don't strictly need connected products, but it certainly makes things easier and more fun and so on. And to just look at perhaps where we're going, because there's a lot of really crappy, to be honest, we won't perhaps all seen this Internet of Shit Twitter handle, which posts all these ridiculous products like this. I don't want to go into that, but to look at something that has undergone very interesting development is our motors. So this is an ad from Sears catalog something in the 1918. That's about 100 years ago. And they offered you to buy a home motor for about $9. That's about $160 today. So to this motor you would buy accessories like a fan and so on, and you would connect it to this, and this would be the motor that you had in your home, the one motor to end all problems. And so if you move forward 100 years, we have a typical Swedish car and a typical Swedish home. This may or may not be my living room. So if you look at the car, how many motors does this car have? It's probably around 50 to 100. And how many motors do you think there are in a typical Swedish home? This is actually a pretty poor picture, but this is from the Royal Palace. So that doesn't really look like there are many motors there. But in my kitchen, I counted at least 15. So motors are everywhere. And we don't think about them. They're ubiquitous, they are small, they're cheap, they're inexpensive. And when motors were new, there were probably a lot of these really crappy applications which people mocked. Oh, you have that kind of motor thing. But some of them just faded away and so on, and what we have today are the crucial ones, the ones that make our life better, and so on and so on. So a connected product, well, it has to be smart, of course, have some computing capabilities. It needs to be connected. It connects to something. It could be your app or your phone or the internet and so on, so that the product itself becomes larger than its just physical appearance, just a physical thing. So it might look like this, familiar examples, the Nest Smart Thermostat and the Tado Smart Thermostat. Well, that's not the thermostat. Really, that's a sensor, I think it is. Or it could look like this. Large-scale million devices doing smart street lighting or infrastructure, monitoring and so on, keeping track of how buildings settle into the ground when they're newly built and so on and so on. Or they could look like this field. Thomas, you started talking a little bit about this, smart agriculture. And that's something we see a lot of interest in from Singapore. Around that area, they're putting a lot of effort into smart agriculture, smart city, and so on. So the title of the talk is essential ingredients for connected products. So I want to just quickly go over 4 of them that I feel are very, very crucial to a connected product, and then move into a little bit more on the low stuff with wireless. So I found that picture very fitting. The salt and pepper, essential to every food, every dish. Okay, so you definitely need encryption and security, and this is just a picture of a bank vault that had to represent this. When you have connected products all over the place, there's the potential of exposing a lot of privacy-sensitive data, and you don't want just the strange uncle that no one wants to sit beside at family reunions. You don't want him to get access to your health information from your whatever product it is. You don't want somebody to start playing around with the street lights, start doing disco. No matter what intentions they have, they might be very good, they might be very bad, but you don't really want them to do that. So you need encryption, you need security. You of course need some kind of user management because there will be a lot of people using it. Of course you need user management capabilities for the end users, and you need a way to set up for administrators and so on. And so you need to be able to have fine-grained control. You need to be able to revoke access rights and so on to the data. And the next slide is going to be interesting because I think there's a GIF animation. Oh, yes! Okay, so when you have a connected product, you also need to make sure that it's very, very easy to commission it, to install it. You don't want the installation process to depend on some very expensive or complicated tool that someone always forgets in the other car, or just someone knows how to handle. But you want everybody to be able to commission the product out in the field. So what we see is semi guys changing a light bulb. That's probably for security, traffic security and so on. And a device here that's actually, I have one of these here today. So it's standing here and keeping track of temperature and so on, connected to a gateway I have over there. So I'm gonna, when all the talks are over, I'm gonna have a look at the temperature data, and we can see which ones were, a little bit hotter, steamier. Firmware updates. Oh, that one works as well. Perfect. So when you build a connected product, the time from when you finish the firmware and the software and the hardware and so on to actually having the product in your customer hands might be months or perhaps a year. You know more about this than I do. But in any way, you definitely want to be able to update the firmware, the software running on the device, after it's out there in your customer hands. And why do you want to do this? Well, one example is that you want to patch vulnerabilities or problems or bugs. Another one is that you want to add features. For instance, like the Tesla car, they pushed software updates so that you can get new features. Every Tesla car is manufactured with the hardware necessary to be fully autonomous, but it's not enabled in software. But a software update will fix that. So let's talk a little bit about wireless. So it's quite easy to get the impression that wireless is just wires, but or just like with wires, but with less wires. But it's unfortunately very far from the truth. So one of the problems you might come up with is called a hidden terminal problem, and I'm just going to go through a few of these things that you might encounter. The hidden terminal problem is that you have two devices that want to transmit to a device in the middle. These circles represent like an ideal view on how far they can transmit. So both of the devices will try to reach this one, but the result is that they will not hear each other, so will just interfere with each other, and the result is that the third one doesn't get anything, and it's just a waste of RF bandwidth and power. A second problem is that this is not the reality. This is a very, very ideal view on the transmission range, or what it would look like around a device. The truth is more like something more like this. Oh, it doesn't really like red. So this one is supposed to be red. So what we see here is rather, instead of the circle, this is more like what the device experiences. You will have patches and very irregular pattern of how successful a transmission might be, the probability of the successful transmission. And this is always changing, and it's changing rapidly. This might be valid for a few milliseconds, for like a handful of milliseconds, or it might be valid for a minute or something like that. But around lunch hour, when people start using the microwaves or so on, end of Friday, people start streaming those cat videos and so on, that will kill your 2.4 gigahertz. And speaking of 2.4 gigahertz, well, there are a few frequency bands that are free and unlicensed bands across the world. Rather, 2.4 is the only one that's free unlicensed worldwide. So it's very attractive for a product creator to build a product that uses 2.4 gigahertz. There are many problems with this as well. This symbolizes the channels in a 6-low-pan network, with the larger ones symbolizing the three most popular Wi-Fi channels, 1, 6, 11. So we can see that the Wi-Fi and 6-low-pan has a lot of, they're using the same frequencies, except for a few channels that are lucky ones here, especially channel 26. But what will happen is that Wi-Fi, and this is pretty interesting, Wi-Fi, before it transmits anything, it does something called like listen before talk. What it basically does is it starts listening and see if there's anything happening. So it looks at the energy in there. And if there is none, or if it's below a threshold, it itself starts transmitting. So what will happen is that due to 6-low-pan and so on being much slower than the Wi-Fi, your 6-low-pan and Zigbee and so on can basically, if you have a lot of it, can kill your Wi-Fi rather than the opposite. And while we're on the topic of Wi-Fi, so I was at Electronica last week, and so this is not very, very representative picture, but there were a lot. I think there were like 50 or 60 access points, Wi-Fi access points available at the spot where I was. So there's a lot of congestion in the 2.4 gigahertz band. And the other one is scanning for Bluetooth beacons, and there were just so many beacons and just so much stuff going on in the 2.4 gigahertz band. So what you can do is go over to sub-gigahertz, start using 868 or 902, etc. Those are the two most common bands. We also have 433 and so on. What also comes with this is longer range, better capabilities of going through like buildings and so on. 2.4 gigahertz is very much affected by metal. It reflects better on metal, so you will have a lot more interference and so on. It's also attenuated by water and flesh. So yeah, if you have a lot of people, this is gonna mean worse communication. So another thing is that you probably want to use, you would probably need low power. And so this is an example of a device waking up a little bit here and there.
1 minute mark.
Awesome. So this is like a baseline of, round of perhaps 1 or 10 microamps or something like that. It wakes up, a small bump here in power consumption. The CPU wakes up, there's probably some timer or something. And so here you can see why radio communication and using the radio is such a heavy thing for a better operated device. While a CPU doing something, waking up and doing something, sending something over radio is really, really heavy in comparison. So it wakes up and it does a lot of encryption of the packets it's going to send. It listens a little bit before talking. This is a larger packet fragmented into 4 and so on. So it's a lot of stuff. So how do we at Thingsquare try to cope with this? Oh, smack. Can I stop this?
Yeah, just press the start button, but try to wrap it up in a minute so you have time to take some questions.
I will. So we run a 100 node test bed over at the office. We test everything that we update these guys. It takes about 4 hours to wirelessly update all of them. Try out new features and so on. Let's see if this GIF animation works. Oh, perfect. So we simulate larger networks and so on, and try out schemas for conserving power. For instance, this symbolizes the state of the radio and so on. Turned on, turned off, receiving, listening, and so on. So one takeaway is that, sorry, do you want to? So I love this Twitter account as well. So one takeaway is that things are happening very, very fast, and it might be very much faster than we think it will. Okay, so feel free to contact me, ask me any questions, talk about anything. Yes, thank you.